All right. So we are, I'm still planning on a quiz tomorrow, polyatomic ions. I have this up in the journal start class, but we'll actually do it at the end. I'm going to run through some notes on how to name ionic compounds and write their formulas. And then we have a few, I have to finish up the lab from last week on anions and cations, which will also help you, hopefully, help you. The more times you see it, the more time, better chance you're going to remember the ions. And then we'll do a little bit of practice fun silliness, and I'll give you the links again. Should have popped into your classwork feed on the teacher down south that has a scienceinc.net website. So yeah, that is our calendario. So in your classwork stream, yeah, looks like it went. There is a note sheet on how to name and write formulas for ionic compounds. So I've gone back, I left chapter 7, or back to chapter 9 again. And then this set of links, I posted, I couldn't find it. I posted in the classwork a while back, and anyway, I don't know where it was, so I just made it a separate post, and these are all links to those practice flashcards, and I'll get to those at the end. And of course, this was on February 1st, last Monday, a week ago Monday, I guess, about the little silly way to remember common polyatomics, and we'll go through that before we leave today. That's my plan. Any problems last night with the crisscross? Any questions on that? Only thing I was seeing on the few that were getting turned in early was that people were putting subscripts as superscripts. So we were putting either the control comma for going below and control period to go to superscripts or powers. So some people were getting those mixed up, but and then there was one other one. Let me get into my PowerPoint, and then I can use my board. So I'm going to go here. So we're going to start these notes, but I just want to, I'll just start on this page and I can write over it. One issue, and I'm going to talk about it in this lecture anyway, so hopefully it'll make sense. I can't remember what the anion was, or what the cation was. Might have been aluminum. Okay, so aluminum is a +3, and then cyanide. I don't know which one it was with this, but cyanide, you needed more than one. And remember, you've got to make these letters capital because this is carbon and this is nitrogen. So there's two atoms stuck together. If you do the crisscross, you need 1 aluminum and you need 3 cyanides. Okay, and we don't write it 3 times because that's a waste of ink. So the problem that we tend to forget is when there's no subscript on the ion itself. A lot of times people just go CN3. What that means to chemists is it's aluminum, carbon, nitrogen, nitrogen, nitrogen. Okay, and that's not it. It's 3 of these whole little bundles, and so we have to wrap up our little polyatomic ion packages in parentheses. And I'm not going to take off points for that, but I just want to point it out to you that I saw several people forgot the parentheses. Easy to do. It's all brand new. Don't worry about it. We'll get it figured out. Okay. So the process of naming things and formula writing, we're going to talk a lot about an analogy between recipes. So if you want to get your secret sauce made, you have to have everything in the right proportions. If you're just making it for your family or you're making it for multiple people, you have to scale up everything if you're going to have it be the same stuff. taste the same. So we have to keep things in the right proportions, and that's what those little subscripts are doing, is keeping atoms in the right proportions. So we talked about this gentleman back in last semester. Antoine Lavoisier is credited, he was a French chemist who his lovely young wife did translations of his work from French to English. Antoine is kind of responsible for getting everybody on the same page with measurement systems and being careful taking measurements, but he also is partly responsible for the naming system that we've developed over the years. He got us started on, let's all talk the same. Let's all call things the same thing. Let's all measure the same way. Then we can communicate a lot better. And so, of course, he met an unfortunate early demise during the revolution, but his work lived on. All right, binary compounds. Again, binary compounds have two, and we're talking about naming them, and so we're talking about writing out words, okay? And we'll also talk about binary compounds of non-metals later, but for right now, we're talking about ionic binary compounds. They have a metal, which of course gives us the positive cation, and a non-metal or a group of non-metals to give us our anion. And again, these form formula units. Then there's also, a lot of times we don't say this, so we're going to distinguish between ionic bonds and covalent bonds. Ionic compounds, and then instead of saying covalent compounds, I don't know why they don't do that, but they say molecular. Okay, so molecular compounds have two nonmetals, for example, very familiar one, H2O, CO2, both of those are binary molecular compounds. Ionic compounds, on the other hand, are things like table salts, okay, very familiar one, sodium chloride. But again, just two elements. How do you know it's just two elements? Because there's just two capital letters, okay? So that's a big deal, making your capitals. NaCl, of course, is sodium chloride table salt. When you name it, it's very simple, okay? You name the cation, sodium. You name the anion, whoops, no flash there. You name the anion, chlorine. Okay, but because it's in a compound and because chlorine forms an anion, you have to change the ending to IDE. So one little clue that you're either dealing with an anion or a compound is the ending of the name is I. Sodium, it's not sodium chlorine, it's sodium chloride. The tricky ones are the transition metals or other metals like tin and lead that can have varying charges. Remember, we have to use a Roman numeral in parentheses to indicate that charge. And we've already gone over this. This should all be mostly reviewed today because I've talked about this several times, but it hurts to go over it again. Hopefully you know your Roman numerals. We won't typically go past 6. So this tells you the charge on the metal. That means the number of lost electrons. Okay, so the big ones, the most important ones. I'll come back to that in a second. So the most important ones with multiple charges: copper 1, copper 2, iron 2, iron 3, and then both tin, I'll just throw this on here, and lead can form 2s and 4s. Okay, so for our class, for our level, we won't typically do much more than that, but you'll see like chromium +3. You don't usually see a 5. I think vanadium comes in a +3. It just depends on what textbook. And then, of course, mercury has those other charges as well. But these are the 4 that I really want to keep in mind. One of the tricky things with trying to figure out what charge is the metal has is, you look at something like what we looked at yesterday, Fe2O3. Which iron is that? Is that iron 2 or iron 3? The key to figuring it out is to look at the anion. Look at the subscript. The anion will always have a set charge. Oxygen's always a -2. You have 3 -2s, that gives you an overall -6. What 2 numbers would cancel this and get it back to 0? Oh, that must be +3, +3. -6 + 3, of course, is 0. So I know that this is iron 1, 2, 3. Okay, you work it kind of backwards by looking at the anion. Questions on that right now? We'll go through a couple examples here. I know it's early to be thinking about this. All right, let's go through a couple examples. So back in the old days, they used to put stannous fluoride into toothpaste. Nowadays, if you look at your tooth of crust, it's going to be sodium fluoride. But I remember seeing commercials about crust, and they said stannous fluoride. What are they talking about? They're talking about tin, for crying out loud. Tin fluoride was added to toothpaste. Why? Because fluoride is a really aggressive element that will kill bacteria because it's so greedy for those electrons. Anyway, so what is this? Well, I know fluorine is a halogen. I know fluorine only ever has a -1 charge. There's 2 of them here. So that means there's a -2 that has to be canceled. There's no subscript at the tin, so that means it must be tin 2. Okay, fluorine always has a -1 charge as the fluoride ion. So we know it's tin and fluorine. We know it's tin 2 from the formula, and we know we have to change the ending to I. So the proper name, let's see, the new name, the current proper IU, the International Pure and Applied Union of Pure and Applied Chemists name is tin 2 fluoride. Classical name, stannous fluoride, the tin with a lower charge. There's another tin compound here, and it is used in glazing porcelain. So again, you look at this and you go, okay, that's tin. I know it's either a +2 or a +4. Which one is it? And if you don't remember, it's okay still. Okay, look at the anion. Well, sulfur is in the same family as oxygen. It has 6 valence electrons. It wants 2 more. It grabs 2, so we've got a sulfide ion. So if there's 2 -2s, that gives us a net -4 charge that has to get canceled. There's still only 1 understood, 1 tin. So this must be the tin with the +4 charge. So we're always trying to get to neutral. Okay, so sulfur is always -2. Tin must have a +4. So we know it's tin and sulfur. We know it's tin Roman numeral 4 sulfur. And of course we change the ending to ide. So this would be stannic sulfide in the old name, which you don't have to know. I mentioned about hematite yesterday. We looked at a picture of that. It's a common way that we get iron. It's iron and oxygen. It doesn't, it's really interesting. I talked about it in the first period or not, but it gives a red streak on a porcelain plate. If you guys took, any of you took Earth Science, College Prep Earth Science last year, hopefully you remember some of your mineral stuff, but it's an Fe2O3, and this is the example I did earlier. Again, The O, the oxygen's always a -2. So if we have 3 oxygens and only 2 irons, to cancel that and get to 0, they have to have a +3 charge. So this is iron 3 oxide. So it tells you in this particular problem, but the formula would look like this. All right, so that kind of transitions us to formulas. Formulas are the symbols, including subscripts, and if necessary, parentheses around polyatomic ions. But we're just focusing on 2 elements right now, binary compounds, so parentheses aren't necessary. And then this is just silly. OMG! So, of course, this would be backwards. This is actually a legitimate compound. Magnesium and oxygen make magnesium oxide, but the magnesium would go first. But it's funnier this way. Anyway. All right, writing the formula of binary compounds. You write the symbol of the cation. You write the symbol of the anion. Add subscripts as necessary to cancel the charges to neutral. And of course, you're going to remember to do crisscross because it's so simple. It's all great and fine to do the algebraic way. It's all great and fine to try it with dot diagrams. Way easier to do crisscross. And then, of course, remember that the Roman numerals in a name will tell you the charge on the metal. Not every metal will have it because some metals, lots of them, don't change their charge. Okay, so let's try this one real quick. This is an example that does have a Roman numeral. So copper 2 sulfide. Okay, so I know that copper has a +2. I know that sulfur is in the same family as oxygen. It has a -2. So if I wanted to write the formula for copper 2 sulfide, it's just CuS. We're all done, right? Remember, it's not going to be Cu2S2, right? We're going to simplify that. If they have the same magnitude, it's just one of each. Okay, that's the simplest whole number ratio. Potassium is an alkali metal, a +1 charge, nitride. So there's several nonmetals like nitrogen and sulfur that make ions on their own and make ions, polyatomic ions with oxygen. So this is a nitride, IDE. You have to really watch the endings. That means it's just nitrogen with 3 extra electrons. Because nitrogen has 5 electrons, it needs 3 more to get its octet. For this one, now the crisscross is legit, and you need 3 potassiums with 1 nitrogen. That's potassium nitride. So sodium iodide, again, sodium's an alkali metal. Iodine's a halogen. It's going to go together 1 to 1. Those are the proportions. 1 sodium with 1 iodine. Because sodium has 1 electron, iodine wants 1 more. Okay. Tin 2 chloride, we just did that. Potassium sulfide, again, +1, -2. Do the crisscross. Calcium iodide, calcium's a +2, iodide's a -1. One of these, 1 calcium with 2 iodides. Okay. No parentheses needed because they're not polyatomic ions. There's a lot more to this. So I'm going to stop on polyatomic ions right now because I want to do some review, and other classes have less time than you guys. And I heard somebody bloop in, so let's see if I can answer. Oh, no. Okay, thank you, Ava. All right. Questions at the moment? Any questions I can answer? Okay, so when you're using polyatomic anions, it's really the same process, but we'll finish that up tomorrow before the quiz. Okay, let's look at our little silly reminder about Nick the camel. So remember, when we're doing this silly phrase, my suggestion to you is that you go ahead and write it out. Okay? Nick the camel ate a clam for supper in Phoenix. What does that mean? This is going to give us all the polys that have 8 endings. Remember, they 8 more oxygen. They have 1 more oxygen than the 8 endings. And I'm going to do this real quick. So it's a little bit delayed, I forgot. I don't like this. Let me go back to my PowerPoint. Sorry, guys. This is a little bit glitchy, I forgot. It works, but it's, I want it to be a little faster. So I'm going to figure out where the heck I am. There I am. I'm going to slide. Yeah, no. Okay, let's try one. Let's try this one. Okay, so I can write on this one. So, oops. Nick the camel ate, I'm going to make it a capital letters, a clam for supper in Phoenix. Okay, so a couple things to keep in mind. The first letter of this silliness, except for Cl for clam, gives you hydrogen, carbon, chlorine, sulfur, and phosphorus. The number of consonants is the number of oxygens. I don't think I can change pen color. Okay, so 1, 2, 3. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So oxygen does some crazy things. We'll talk more about it in the coming weeks, but it can combine different ways with different elements. Okay? And then the vowels tell you the charge. They have oxygen, the ATE ending tells you that. These are all anions. Okay. 2 vowels. Carbonate has a -2. 1 vowel, -1. 2 vowels, -2. 1, 2, 3 vowels, -3. The 8s are nitrate, carbonate, chlorate, sulfate, phosphate. Ite is 1 less oxygen, so NO2, there is no carbonite, ClO2, SO3, 3, PO4. Oh, PO3. They have the same charge though, okay? So they have one less oxygen, but they have the same number of extra electrons. -1, -1, -2, 3. So from that one silly little phrase, we've got 9 of your polyatomic ions, and very common ones. The other ions that are fair game for tomorrow, the only positive polyatomic, ammonium, super important hydroxide, and for tomorrow, then, I'm trying to think if I wanted to add one other one. Oh, I know what else I was going to, then the other 2 that are related here, remember we can have ClO4 also with a -1, that's perchlorate, and then we can have ClO with a -1, that's hypochlorite. Wow, that's really messy. Hope you followed along. I can make another. I can make a list really fast. The ones you have to know for tomorrow. Okay, so again, I'm going to write their names, and you can write them down as well. Nitrate, nitrite, carbonate, chlorate, chlorite, sulfate, sulfite, phosphate, phosphite. Who am I forgetting? Next, hydroxide, ammonium, and then perchlorate and hypochlorite. So that gives us 13. You can test it on 10 of them. Okay. Questions I can answer right now. Anybody? Good. So we still have a few minutes. If there's no questions, I want to show you, this is from this document that I put in, polyatomic flashcards. You can quiz yourself. There'll be more on in this stack than we're going to be tested on tomorrow, but you're going to need to know these eventually. So again, you can go from the formula and try and guess the name, or you can get the name and try and guess the formula. I'll explain how to get these hydrogen ones at a later date, maybe tomorrow. Okay, and then hopefully you'll recognize some of these. So you can quiz yourself this way. I'm not going to test you on acetate tomorrow, but this is an important one. Ammonium for sure, nitrite, nitrate, sulfite, sulfate, hydroxide, phosphate, carbonate. Actually, all but acetate on here. This would be a good deck to get some of them. And then the last one, this is another little game. If you like to play concentration, this is kind of fun. It's a little bit tricky, but I'll show it to you. Usually in class, we go ahead and try these. I'm terrible at this. Ah. Yay, I got lucky. All right, so I know that's chlorite. I didn't see that yet. That's acetate. Ooh, I got that one. Anyhow, we would normally try these in class and see who gets the fastest time. Oh, heck, I saw that. Like I said, I'm really bad at this. So you can try and, yay. You can try this on your own. It's good practice. Anyhow, I've had people get under a minute lots of times. Oh. Come on. Like I said, I'm terrible at this. So, oh, I saw that one. Where was it? Oh. So, good practice. Have a little fun with it. I'm sure you can do better than I can. Okay, I'm going to stop recording and see if there's any questions.